Like, what happens when somebody way up in user land opens a file?
Okay.
Can we step through that?
So let's, I'll erase my scribbles so far here. Okay. So I will draw back up here this is going to be our system cache virtual address space. And for our purposes, I'm just going to say, there's some addressing mechanism. It starts at 0 and ends someplace higher. It actually will never start at 0, but it's actually always going to start at the high bit will always be set because it's a kernel virtual address space, and all kernel virtual addresses have the high bit set. So on a 32-bit operating system, this will be 1, 2, 3, 4. That's the lowest hex address that it could possibly be. It's actually always higher than that, but
That's fine.
another point altogether. So the files. So the user calls create file, and they open a handle. So you have, and this is what the application sees. They see their handle, and it has some number. Handle 15. When this handle, then they call, say they call 132 read file. This handle gets translated when it goes into kernel mode. So we'll say this is up here is in user mode, and then we move to kernel mode. When it comes to, it'll come into the kernel, and basically it'll be talking to NTFS, which is the most prevalent file system on Windows XP and later today. So this is our main file system, and it comes in, and at this point the handle gets translated from a handle to a file object. And the file system in that file object tracks all of the information about where it is on disk, what its name is, all of the it can, from a file object structure, the file system can get to the pieces about that file that it needs. So it sees, and the file system is also tracked in this file object. When the handle was open, when the file was open, the user specified if they wanted it to be buffered or non-buffered, unbuffered I/O. And so if the user opened the file handle as a buffered handle, when the read comes through, the file system will say, I need to use the cache to read this data. So on the read, the file system will end up calling a routine called ccopyRead. And to that, it gives the file object, the file offset, and the length of the data to read. And this is the cache manager. The prefix for all of the cache manager routines is CC. So the cache this is a routine that's implemented by the cache manager. The cache manager then sees this read. First, it goes from the file object. It goes to its shared cache map, and it looks up the view. In the shared cache map, we have basically a mapping of file offset to view in the VA space. So the shared cache map will look and say, this data resides in that portion of the system cache. And then we do the translation of the file offset to, so if that file offset is 100 bytes into this view, we reference 100 bytes into this virtual address range and read the data from there, copy it to the buffers that were passed to us by the file system, and the file system sends those buffers back to the user to their read. That's the easy path when the data is already in the cache. If the data is not in the cache, we have to find an empty view, call the memory manager to map that range of the file to that specific area of the virtual address space, and then we can start using the data. And on reads, There are two flags that are exposed also through Win32 when you open a file that specify how you want to use the file that hint to our read-ahead capabilities. And those two flags are file flag sequential scan and file flag random access. If you specify sequential scan, that's the hint to the cache that you're going to sequentially read this file. And so when we see the read, we start reading ahead from that position. And we'll read more aggressively ahead if you specify a sequential scan. If you specify random access, we're not going to do any read ahead at all because you're going to randomly access the file. So we don't want to potentially waste the resources pulling in data that you're unlikely to use. If you specify neither of those flags, the cache manager tries to guess based on the patterns that your I/O pattern, what you're doing, and it can detect sequential forward reads, it can detect sequential backward reads, and it can detect strided accesses. So if you access something at 10 bytes at offset 0, then 10 bytes at offset 10,000, then 10 bytes at offset 20,000, we'll start reading that. In those cases where we're basing the read ahead purely on monitoring what the user's doing, we don't read ahead as aggressively in case we're wrong.
And of course, you're talking about a user is really Win32 that's making calls into you on behalf of a human.
Right.
But it's the Win32 that's giving you the information of the flags,
Right.
obviously, because the average user doesn't really know what a
Yeah.
sequential
That's
read is.
true.
Let's see.
That's true.
How would you like us to read this file for you sequentially? I don't know. That's
Yeah,
cool.
so a lot
I
of
just wanted to bring it up, and it's a good
true.
point because Win32 really is just a proxy to kernel land,
Right.
because you don't want to really make kernel calls directly, although you can on NT.
Right.
So Win32 is this nice abstracted layer away.
Yeah, it was just really, that layer just allows you to write applications that worked both on the Windows 9X platform and on the NT platform. And so maybe someday we'll be able to throw that all out
Yeah.
and just use NT because there's, but unlikely. I don't know.
Patterns dictate that probably won't.
Yeah, probably not.
Kernel bang open file. I think.
Well, all of the layers of security and such, there's actually, there's a few things in between here. And so it's just called, all of the kernel interfaces are exposed in user mode through what's called NTDLL. So it's really just calling a different set of interfaces. All of the same security checks and such are still are gated at that point. So
They are. So if you call it directly, there's still you
Yeah.
can't get around security.
exactly.
But what would be one of the disadvantages of doing that? Could you crash the system if you
Uh.
did something incorrectly?
No, it's just that the NT interfaces expect things in a way that wasn't compatible with Windows, the Win 9X world. Like for the way files are named, actually, or how you get to devices, is different, and that translation is done in the Win32 layer for you. So.
Well, it's certainly. It's just good to know how much really happens when you just open a file.
Yeah.
It's great.
Yeah, the opening a file is actually quite an expensive operation compared for the file systems. There's a lot of data that needs to be read to find where your file exists. All that the name parsing, and that can cause basically bringing in a number of pages of the files that track the on-disk structures that NTFS uses to track where files sit.
So I'd imagine that some of the bugs that you've encountered could be really interesting up in user mode when there's a bug in the cache manager and you're looking at maybe wrong places in the cache or open a file.
We try not to let those happen. But generally, I say like most of the bugs I deal with, they're either really easy because if you screw something up, you find it out right away. Things get corrupted. Your machine doesn't boot. If you do something, you don't get very far if you make a very obvious mistake. It's really the subtle mistakes that are much more difficult to find. You can have subtle timing issues that cause data corruption very infrequently or only on certain hardware with very specific timing characteristics to hit them. And I've had a number of issues that I spent months, if not years, just tracking because they hit so infrequently.
Wow.
And then when we try to put in instrumentation to figure out why it's happening, it goes away. And so we have, you go through this iterative process of, can we find a better way to repro the problem, or can we find can we strip down the instrumentation to make it less intrusive, so it will be less likely to interrupt the timing. And sometimes you're just lucky. You finally hit on something that, because once you have a problem that can repro in a relatively short amount of time, like on the order of hours, there's a good chance you can find the problem. When it repros once every 2 to 3 months, you're going to find the answer, but it's going to take you a long time to get there. So,
Sure.
And even in a product such as Windows, where our ship cycle is relatively long, it's still, you can have things that lurk for a while. And the other thing that's interesting is that with the new hardware, new generations of hardware, it's faster,
Yeah.
more parallelized. You find new problems in code that's been working fine for 15 years. And then just because now processes are faster, you get more parallelism between multi-proc machines and then hyper-threaded processors.
Sure.
There's just more timing.
The multi-core.
The multi-core, exactly. Yeah.
Now, is that really going to have much of an impact on you? I mean, since you're already writing highly concurrent and...
It doesn't change the code per se. We find as it's more common for people to scale and as the hardware can scale higher, just the issues of our software scaling across the operating system become more interesting. It used to be that just having 2 processors in your machine was very, only high-end servers had that. Well, now, you go buy a laptop and you can turn on hyper-threading. So, and that then translates, that means the high-end, very expensive servers have many more processors, can have 16, 32, 64 processors. And the Windows team there's an entire team dedicated to tracking performance. And they do a lot of analysis on hardware and find out where our bottlenecks are and help the different teams figure out where those are and what we can do to address them to help.
Now, is there a processor barrier for Windows or NT? Like only so many?
Oh, the maximum number of processors?
Yeah, is it 32 or 64?
I don't
it's
know.
64.
I think it's 64, but I'm not sure.
That's an awful lot of processors. For the super high-end systems.
Yeah.
So if it's 64 is 64-bit, that's insane. Great. Well, that's clearly very deep.
I guess one thing I actually haven't spoken about, which
Sure.
is another piece of the cache manager
Great.
that people don't always understand, is that so the read we understand. I've given examples of read, but the other side is when you write data to the cache, it's buffered on purpose to help. If you're going to write the same data multiple times, we'd rather not write it to the disk multiple times, and that's what the system cache, the benefits of the system cache. But so that means that when the user has said write file and it returns, the data is written to memory but not yet written to disk. And so how does it get written to disk? Is a common thing that people should wonder. So
Absolutely.
First, you can explicitly tell the file to flush, and then it will get flushed. But we also have a way of tracking so that applications don't have to do that themselves. The cache manager has a series of threads working in the background that are called lazy writing threads, and they just basically lazily flush the data that's modified in the system cache.
Now, can you explain lazily? It's not randomly.
It's not randomly. It's just we just periodically wake up and say, oh, we should write some more data, and we track, and then we walk through. We keep a rough LRU type list of when the data has been modified, and then we actually have a cursor that walks through all of the. We link all the cache maps that have data that's been modified in the cache together, and we just walk through those a little at a time. Walk through each file at a time, and we have a target number of pages that of pages we want to flush, physical pages in memory we want to flush each iteration, and so we select the files and then issue the flush through the memory manager, who then writes the physical pages out to disk. And so it just, the algorithm, it's basically a heuristic where if you're writing a file, in about 8 seconds, all your data should get out to disk. There are places where that doesn't hold true, like actually for temporary files. We never flush temporary files unless we're under memory pressure.
Okay.
So, because the user said it was temporary, so we don't want to keep it right to disk. If they often just close it and delete it. So we'll just bypass writing it to disk altogether.
Yeah, that brings up an interesting point in terms of how you communicate with. So the memory manager would let you know that there's memory problems. Like,
Right.
right. So does it fire an event? Is there that sort of kind of in
No,
kernel
there's
land?
actually checks based on. So if the cache manager and memory manager are essentially siblings in the kernel, so they have routines that each other can call. And there's a routine that the cache manager can call to say, we can see if there's enough memory available to let more data get dirtied in the cache. And so we can tell if and if there isn't, if we're under sufficient memory pressure, we'll start holding up cached writes until we can get more data written to disk. Because you can clearly write data to memory much faster than you can write data to disk. And so if we just let cached writes happen unbounded, you would eventually be out of memory. Yes. So we have a way at the cache manager level to block writes until we have enough memory available to let those writes through.
And you keep them in a queue.
And we keep them in a queue. Or we block the thread depending on whether or not the write was synchronous or asynchronous.
Right.
But then, so with that feedback, plus we track, we have some rough heuristics on how quickly data is getting data is getting modified in the system cache, and that all goes into our calculation of how many pages how much data we want to try to write this scan, and so we do that, and we just the lazy writers just continually walk you through the list of dirty shared cache maps and trying to find pages to flush. The benefit also that the system cache gives you here, if you're writing to a file randomly, the lazy writer will always flush the data sequentially as it's dirty. So it'll start at offset 0 in the file and go to the end of the file and only flush the ranges that it knows are dirty. That gives you more efficient writes to the disks, less since the file systems ideally have allocated the file contiguously on the disk, we have more efficient writing patterns.
So now, how long have you been working on the cache manager here at Microsoft?
I've been working on the cache manager for about 2.5 years now. I have worked at Microsoft for coming up on 6 years now. So, though I've always worked in the file system team on various things, though never directly on a file system, interestingly enough. So, I actually was, when I started working on the filter manager project with Neil Christensen. Yes, right. So Neil and I did most of the architecture for that. And then I wrote, for Windows XP, I wrote the file system filter driver. That's part of the system restore feature of Windows XP. And then I moved on to the cache manager. So I still am quite involved in the filter world.
Sure.
Neil doesn't let me run very far. So.
Well, I noticed his office
It's right
next
next door to
you,
mine,
so.
yes.
So how, could you just quickly talk about the filter manager and XP System Restore?
Yeah, so so I'll start with System Restore, because that's probably something that people are pretty familiar with. It's today, yeah, and it's more visible. So the System Restore it's a feature that allows really simple recovery of your system configuration is the goal. So things like you install, and the types of scenarios it was supposed to help is you install some new application and it makes your machine unusable. You want to roll back. Maybe uninstall doesn't work right, or you had twiddled with a number of settings trying to get it to work and you gave up. You want to roll back to, you knew it worked yesterday, I want to go back to yesterday. So System Restore allows you to do that. And the way System Restore allows you to do that is it basically takes snapshots of the system at various points in time, of the basic system databases that control the configuration. So the registry hives, some of the COM databases. There's a couple other databases that are kind of describe the core configuration state of the machine. But we don't really have the disk space, and it would take too long if we wanted to also snapshot all of the system files, like everything that's in your Windows directory and program files directories. Like you don't want to, I mean, that's a lot of data, and we couldn't copy that in any reasonable amount of time. So what the filter driver does is sit there and watch files as they get modified and see if they fit into the set of directories and file extensions that we have denoted as system files. Okay. So if it sees a .exe, a file with the extension .exe, will copy that to the restore location. So then we end up only having to save off a much smaller set of modified files. Sure. For each restore point, each unit that you can restore to. And so then when you say you want to restore to what it was yesterday, we basically copy all of the files the original versions of the files back to where we copy them from to replace the changes that have happened in the last day and replace the databases. And there's a little bit other patch-up work to make sure everything still works right with, if you've changed your password and things like that. So we don't want to revert your password. So
well, that's a great feature.
But it's very useful. And it's kind of in my world where very few people know what I do or I can't explain to my mom and dad exactly what this is. System restore is something that the family members understand.
After this
yes, exactly. But system restore is something that people pretty commonly use, and usually when it works for them, people are really happy. So.
Well, it's like, that's really the way it is in kernel in general, right?
Yeah.
Everybody upstairs doesn't really pay a lot of attention to what's going on in the kitchen. They like the food that comes out.
Exactly.
And so that's one of the things we're trying to do with going deep. Making it. I think what you talked about today is very understandable to even non-architects and engineers. Excellent. Now, you're probably the only woman on the kernel team as a developer. Is that true or incorrect?
I don't think I'm the only woman, and there are, I think, a handful more, but there's not too many of us.
So what did you study in school?
I have an undergraduate and master's degree in computer science. So.
And operating systems was your?
It was actually something I fell on late in my career. So.
Oh yes.
I can sit down. I actually moved to Seattle to go to graduate school at the University of Washington. I was was in the PhD program and was going to be a professor because that's what I wanted to do. And I was actually, my area of interest at the time was software engineering. And I always was interested in the complexity of building software and how do you build that reliably. And then I got involved in that, and I found out that studying how to build safe systems wasn't really quite as interesting as building them yourself. And it was actually my graduate level operating systems class that I just found fascinating, and and I decided that's what I really want to do. So after I finished my master's degree, I decided to take some time off and go work at get a real job for a little while, see what that's like, instead of deciding whether I was kind of making a decision if I wanted to stick it out for another few years to get the PhD. And I tripped on to I worked actually at a startup here in Redmond for a little while, and then decided that I didn't really like industry better than academics for myself, and but I also wanted to work at a larger company. That company was very small; it was only 6 people, and almost, I think all of us at the time were like under 30 or under 31. I wanted to work someplace with a little bit more experience.
Sure.
I could learn a little bit more, and so I came and interviewed at Microsoft. And I must admit, my arm was kind of twisted to interview at Microsoft. I had this vision that Microsoft was this, horrible place, and it was very competitive, and those interviews I just heard were horrible, and I just didn't really want to go through that at all. Yeah. But a friend of mine convinced me, he's like, oh, it's just a day. How bad can one day be?
Just 10 hours.
Exactly. So, and I didn't actually, I was very pleasantly surprised. So, I interviewed with the file systems group, and all of the people were super nice and very friendly, and the work they were doing sounded really interesting to me. I didn't know a whole lot about file systems at that point in time, other than what I learned in school. So I didn't have, and actually at that point I had no experience writing kernel level drivers. I had done kind of low level application communication type work at the company I worked at before here, but it was not kernel drivers. So I came in and had a lot to learn.
Sure, and you probably quickly, your first bug when the system crashed, you quickly understood that, all right, I really got to be careful.
You got to be careful. And
You got to be a really great programmer. Bottom line.
Yeah, there's not a lot of room for it. You can't be sloppy. That's the one thing that there's not many safety nets there. But at the end of the day, writing good code is, wherever you write it, you should write good code. So it's,
Sure.
All of the things that I had learned in school and in, summer jobs and all these, they're all still applicable.
Yeah.
Good design concepts and all of those things are still applicable. It's just a different environment and a different set of tools to learn to use. Learning how to use a kernel debugger was a bit of a challenge.
Sure.
But you learn how to do that, and then it's just the same as using the debuggers that you were used to. Yeah.
So, do you see, I was been raving about this probably theologically perhaps, but we seem to be at a point in history where the operating system seems to not be evolving. The operating system. NT is great, right? We have Linux and Unix, you have these different things, they're all basically the same as far as core architectures. That could arguably, it's not true, but it is. They're all based pretty much the same. Why do you think that is? Do you think that's true? Do you think operating system research is dead?
I don't think it's dead. I think you're going to the operating system, it depends on how you want to define the operating system. At some level, every operating system needs to provide the same interfaces to devices, getting the hardware to do the basic core set of things. And that core set of things is actually quite large and takes a lot of effort to get going and get correct and keep it correct and keep it performant as the hardware changes. And that is an ongoing task. It doesn't end once you ship your operating system. But in Windows, we're really interested in providing a rich platform, which is the operating system, the core operating system kernel piece is basically the foundation for the rest of that work. And so we have to keep that foundation strong, and as the hardware changes, as the demands on the system change, as just what the user requirements change, so that we can provide a good and interesting platform for people to develop on.
Absolutely, and you want to be as in other words, you don't know what people are going to do up there.
Right.
So you want to provide the richest field for people to explore. That's interesting. Yeah, I think mine's more of an esoteric academic thing. I'd like more of an intelligent kind of thinking operating system. But what does that mean? I don't know. But it's fun to talk about. Well, this is great. So you have a lot of bugs trying to fix?
No, we're getting pretty low these days. We're about
You're
ready
working
to
strictly
release.
Longhorn right now.
No, I still work a bit on the Server 2003 Service Pack 1, kind of closing up the final bit of issues. We don't, the development teams, at least my experience with development teams in Windows, there's a sustained engineering organization, but we work very closely with them and with the product support engineers when the customer issues come up that they can't solve.
Understood.
And there's me working solely on the cache manager, but they have most of the Windows sustain engineers and the product support people. They're experts in a much wider swath of things. So it's not shocking that when the issues get intricate enough, they don't know the ins and outs to always figure out what the problem is. But so I spend a good amount of time
helping them.
Helping that. Yeah.
Do you ever go on customer visits?
I do not.
Okay.
No,
Yes,
I've
I
been,
think-
I guess, fortunate enough so
Yeah.
far that I.
Well, it's not really kind of like you don't plug into the cache manager, right? It's not
Exactly.
it's not a platform.
Yeah. I do. I mean, the main at the interop events that we provide for file system filter writers and file system third-party file system writers. I've given talks there about the cache manager, but it's not. Most people don't buy the operating system for the system cache, but they're not very happy if it doesn't work
Exactly.
well for them. So
Precisely.
not a line item on the box, but
No.
it can't be broken either.
No, well, I mean, it seems like it's working great. And you're the only person working on it.
Yes.
And do you have a tester, a couple testers that help you? Or?
Yes, I have one primary tester, Rudwig Bach, who works with me.
Okay. Who's probably also a developer.
He's a software design engineering test. So
Fantastic. Well, this is great. I now understand the cache manager, which
good.
means probably most of our audience does. And thank you very much.
Oh, you're
Appreciate
welcome.
it.
Well, thanks
your
for having
time.
me.
Say hi, Mom.